So to talk about integrable models, I will give a very specific definition, which is not rigorous, also because there is no rigorous definition of integrability in quantum field theory. And I will not talk about the most interesting things, like what you can do with it and all the interesting mathematical structures that exist in integrable models and that allow you to go a long way towards solving them. But so for me, integrability would be the existence of an infinite number of conserved currents, which I will label with an index, and I require them that they have increasing spins, and and moreover they should generate commuting charges. And so this is a definition of integrability that I want to stress. It's strictly two-dimensional. In dimension greater than 2, you can prove that if you have these conditions, essentially your theory can only be trivial. And if you have heard the statement that n equals 4 superior mills is an integrable theory, which is an interacting CFT in 4 dimensions, that indeed is very true, but integrability there appears in a slightly different way. What I would like to discuss now is that in two-dimensional CFTs there is such a structure. We've seen that they have an infinite dimensional algebra, the Virasoro algebra, but it's a non-abelian algebra. But inside the algebra of all products of Virasoro generators, there is an infinite dimensional abelian subalgebra. And then we'll see that this gives interesting structures when we perturb the CFTs with some particular relevant operators, and we get integrable models. So in a CFT, it's very easy to find as many conserved currents as you like, because so you have the Verma module of the identity, which is completely factorized into holomorphic and anti-holomorphic part. So any field in the left sector would satisfy this equation. But then, okay, it's a bit more difficult to show that you can construct commuting charges. Okay, I will consider the case where there is only the Virasoro algebra and there are no other structures like W algebra. But so you find that you can define these currents, and I will denote them as Ts plus 1, where S will be an odd integer, and S plus 1 is the spin of the currents. And so they appear at level S plus 1 in the Verma module of the identity. And so they will define some charges PS in this way, and these charges will be commuting. And well, I will not show you that this structure is there, but for example, the first one, T2, is just the stress energy tensor. And then you find one at every level, and the restriction is due to the commutativity. And the next one, for example, is L minus 2 squared acting on the identity. And if you see what this is essentially the regularized square of the energy momentum tensor. So it's the regular term in the OPE of T with itself. And then, so T6, for example, there will be a particular combination of well, you get essentially always regularized polynomials in T and its derivatives. And this structure continues. And now we want to study a relevant perturbation of the CFT. So yeah, why there are no odd spin currents? Well, let me see. I think they will kill by the commutativity, but maybe there is a better argument.
Can I also ask a question?
Yeah.
Should I be surprised? I'm a little bit confused why you just have negative modes there. Is it in general the case if you wrote T6 in terms of modes, you would have some product only of negative modes? I mean, I can see that it has to be something normal order, but why is something where the total mode number is, in this case, minus 4? That's maybe a little bit surprising, or maybe not, I don't know.
Maybe, can we let's discuss this later. I'm not sure, I don't know. I know the answer.
And the other thing, you mentioned that this is the case without any W symmetry. If there is a W symmetry, is there some understanding of what the story would be? Or is something that people just consider?
My understanding is that this follows on, so this will be there. Actually, this depends only on the Virasoro algebra.
For the other spins, if you have some W symmetry, then you generically get.
Oh, you get more currents.
More currents.
Yeah.
And they would have the, you've got even or odd.
I would say that they're odd then.
So you get an even one.
Okay. Yeah. And by the way, so maybe I should mention, because the school was on CFT, and there are some lecture notes from a past edition of the schools where by Stefano Negro, where it's all on the integrable structure of CFTs. But okay, the case that I want to consider is where I will perturb the CFT with some relevant operator. Okay, so now let me maybe stress again that so this will be a benign perturbation that will give us a well-defined quantum field theory, not something crazy like T-Bar. But and we can do conformal perturbation theory, and this tells us exactly how these equations of motion are perturbed. So of course we will break the holomorphicity. So if we study one of these currents in conformal perturbation theory at the first order, you get a correction to the equation that before told you that this was holomorphic. And I will not prove this equation for you because I don't have time, but where you integrate over a circle that goes around T. So you see, this is essentially, you need to select the pole in the OPE of these two operators. And then, so to say that the current is still conserved, at least at the first order of perturbation theory, you want this thing on the right-hand side to be still a total derivative of something, essentially. So if you do it for the first current, well, you get this. And okay, you can do it with the OPE that you know very well, and you just get this strange factor because you are expanding on a different point. And you get a contribution also from the double pole. Well, so this tells you that, well, first of all, this factor better be there, because if you have a marginal perturbation, then you don't spoil the holomorphicity, because then delta minus 1 is 0. Okay, but then it's a total derivative, so it's fine. The stress energy tensor is still conserved. If you try with the next one, well, I need to copy it. And you get this. So you see, you always need to get something that is a descendant of phi. And in this case, you get a level 3 descendant of phi.
On the second equation, there is an integral, and the phi is the fact that's excited.
Yeah, so this field phi is it has a 0 spin. So it has the same left and right dimension, because I don't want to break rotation invariance in the theory. So it's essentially, like the product in CFT, it's a product of two fields. One depends on Z and one depends on Z bar. Yeah, well, yeah, so so you have to think of this as a product of two things. One, I can put it at the same point already, because it's the anti-holomorphic one, and it will not have any singularity with T in CFT. Yeah. Okay, so you see that here we have a problem, because so the total derivative in CFT is L minus 1, and we cannot factor an L minus 1 on the left. So this current in general is spoiled, and so the situation gets better if you have in your spectrum you have some degenerate fields. So in particular in this case, if you have this field that you saw in Sylvan's chord, so that phi lives in a degenerate representation, then this field at level 3 satisfies BPZ equation at level 3. And then this equation that tells us that one of its descendants is 0, if you combine it with that one, you can now factorize an L minus 1 factor on the left. And you discover that this current T4 is still surviving the perturbation. It's still conserved.
Sorry, what is written there?
So here, okay, there are some coefficients that depend on C and on delta.
What's the subscript of the first term? Is it L?
Minus 1. Sorry, this is L minus 3.
Okay.
Yes. Well, okay, so if you combine this equation with that one, essentially you can find that this T4 is equal to this Z of theta2. You find explicitly this new field and this new conservation law at first order in lambda.
Sorry, I'm a bit slow. You want to eliminate the L minus 2 and, from that equation? Is that what you want to do?
Yeah, you see, you can use the Virasoro algebra to rewrite L minus 2, L minus 1 as you bring L minus 1 to the left, but then you get an L minus 3. And you want to kill the L minus 3, and you can do it with this equation. So you want to have L minus 1 of something.
So that you end up with an L minus 1 to the left of everything.
Yes, which is a total derivative.
But then you can only do this if you choose your deforming operator to have exactly that dimension.
Exactly, yeah. So only if you deform with some particular degenerate fields, your new quantum field theory will be an integrable quantum field theory. That is the statement. And well, and essentially, the homological found that this pattern continues at other levels. So there are some restrictions that you need to have, because, for example, the dimension of this field is real only if C is less than 1. And it is relevant in this range. And you can consider also delta minus 1, 2, and delta 2, 1. These are the relevant perturbation that he considered. As essentially, he proved that they preserve integrability, or conjectures. He checked it for many levels, and also you can have an argument that essentially this first order in conformal perturbation theory essentially gives you everything, because because of scaling, because you can imagine that this equation is corrected by other terms now. But you see that lambda, this lambda now is dimensionful, so it has a positive dimension. And to match the correct dimension, you need fields with lower and lower dimension. So for sure, you can say at some point it will truncate if your spectrum is bounded below.
Sorry, and degenerate is like marginally relevant dimension less than the but still makes conformal.
If it's
If it is marginally relevant.
marginally relevant. I think then it would be much more complicated to make this argument, and probably you cannot use the one loop argument.
Sorry, you assume phi is primary.
Sorry?
You assume that phi is primary.
Yeah, sorry. Phi is the primary field in a Verma module. Yeah. Well, I wrote these two fields because they're also turn out to be integrable. But you can see that, for example, delta 1, 2 will not allow you to save the current T4. But it will, the current T6, on the other hand, would still be preserved by delta 1, 2. So each one of these perturbations will give you essentially a pattern of spins of your integrable models where the currents are. So for this perturbation, you get that these charges will still be there, where the spin is all the integers, and delta 1, 2 will give you a different pattern where the spin essentially, well, let me write it like this. It will be 6 times k plus minus 1. That's the pattern. Well, it's starting from 1. Yeah, so I'm using, my notation is that is Ts plus 1, and it gives you the current Ps. So T4 gives you the current P3. is the dimension of the charge. Yeah.
Sorry, Andrea. Just one. What is the generic pattern? Whenever you arrive, I need to correct it with the second level BPZ. If you want to generate T6, what happens to it? Should you correct again? You wanted to generate the whole tower and then check that this is indeed integral, right?
Yes.
Right, but I mean, are you correcting every level or how, what is the generic pattern?
Can you repeat the question?
Can you repeat the question? Then I repeat.
So the point is that you are correcting T4, this T4 with the BPZ level, second level, right?
Yes.
So do you do this to every next current or every next to next? How it goes?
Well, you try to do it for all of them, and you see if, in principle, you can take the approach and compute and see if some of them persist.
Maybe one way to.
So you use the same BPZ equation to prove
I think that was the question.
Yeah, sorry, that's the question. Yeah, so with this field, using the same BPZ equation, depending on what you find at the other levels, you will see that they're all preserved. Yeah. Okay, so yeah.
Tensor-T2 is equal to 0. That's the one. And Tensor-T4 is equal to 0?
No, you want to show that you can have some new conservation laws that are not related to holomorphicity, that have the form that d plus 1 is equal to dz of theta of s minus 1. You want to find a new equation like this. Because this will give you a conserved current, then, well, you need to, according to my initial definition, you need still to check commutativity of all these charges. Okay, so let me give you some example. Maybe, so if you take the Ising model, and in the spectrum, yeah.
Is theta related to the trace of combination of traces of T somehow? Like
For the higher ones, I don't think so. But for the stress energy tensor, yeah, essentially with the first equation, you see that theta is equal to 5.
but for higher ones, it's not.
No, I don't think so. Yeah. Okay, the Ising model. So in the spectrum, this has the fields delta 1, 3 and delta 1, 2. And so if you perturb it with this one, this is called a thermal perturbation. And so this was originally a massless free fermion, and this is very boring. It just becomes a massive free fermion. But this one is much more interesting. So if you perturb it with this magnetic perturbation, you will get essentially a theory that in an infrared has 8 different types of particles and some very non-trivial S-metrics, which even has some emergent E8 symmetry. And then, of course, you can say, I perturbed it by a mixture of these two, and then you will get something non-integrable that would be much more complicated than these two models. Okay, so
What if you start from something even simpler, say three boson?
I think you need to have this, but I don't know if you, yeah. And so I think you can do it for the Liouville theory at C less than 1 that Sylvain told us about. And I think in that case, if you do delta 1, 3, you get sine Gordon. Okay, so the way that you solve these integral models typically is by a bootstrap approach, and by showing that for these models, you can do a bootstrap for the S matrix when they describe massive particles. So I want to show you why in this case, the S matrix bootstrap, which is the idea of constraining the S matrix by the analyticity and crossing symmetry unitarity, becomes much simpler for integrable models, and you can solve it exactly. So if you imagine that you have a theory that in the infrared describes particles, so we're going to end the school as far as possible from CFT, actually, talking about scattering of particles. And, well, in principle, of course, you don't know how to connect the infrared with your UV description that we discussed now. But so what you know is that when you have these higher spin charges, you not only have the conservation of momentum, but you also have conservation of some objects like this. Or this. For the particle K. And essentially, if you have something like this, you can see if you have it for enough values of the spin, it constrains your dynamics enormously. And essentially, you're forced to have the exact same set of momenta outgoing and ingoing. So essentially, the scattering has to be something like this, where there is no deflection or creation of particles or annihilation or anything like that. The momenta are exactly the same. You just have some two-body events happening. And you can restrict your S matrix bootstrap to study the two-particle S matrix. Well, in this case, essentially, you can solve many models by classifying the solutions to this S matrix bootstrap. And what is the connection with the T-Bar story enters through something that's called CDD factors. So essentially, these S matrices, if you take the axioms of the bootstrap, they have some ambiguity. That you can take your two-body S matrix, at least formally, you can multiply it by something like this. Oh, I didn't introduce this P plus minus notation, but this is the light cone momenta. With a combination of these phases. And so characteristically, you find that these S numbers that enter here, they have to be the same set as the spins of the currents of your integral models.
Sorry.
And this is non-trivial to see.
They're all the same S's for all the P's. In a given term.
Yeah, they are, because otherwise you would break rotation, Lorentz symmetry in 2D or rotation symmetry. Yes. And well, the connection of this with T-bar is that one of these shifts where S is equal 1, this gives you the T-bar deformation. If you take your S matrix and correct it with this phase, and then plug it into this thermodynamic Bethe-Ansatz machinery, you will derive this equation for the deformation of the energy levels of the cylinder that we saw at the beginning of the first lecture. And also, this particular dressing of the S matrix is the only one that you can generalize to a non-integrable model as well. So you can essentially take a any S matrix of any theory, and then you just multiply it by, so if you take an S matrix with some now any sets of ingoing and outgoing momenta, and now let's just multiply it by everywhere but this phase. Where I take any pairs of particles, so and you can see that, well, it works only in 2 dimensions where you can introduce some ordering of all your particles, but formally it will satisfy all the requirements of the S matrix, except for the fact that, of course, it looks very bad at high energies. But this is conjectured to be equivalent to the T-Bar deformation for a generic non-integrable models, while the other currents will exist only. These dressings, you can do them only for integral models, because to show that they satisfy healthily your axioms, you need these conservation equations.
You also have an S in front, like in the previous slide. That also is a new factor in front of the old S, right? So I'm not sure the notation that you have there is S. Capital S. Capital S, the S matrix.
Oh, yeah, sorry. Yeah, this is, it's a phase that, yeah. Yeah.
If you have an S that satisfies your axiom, then you can get a new S that satisfies that.
Yeah. And yeah, can you? Sorry, I always get confused. How much time do I have?
10 minutes.
10 minutes. Okay. Well, so for essentially, there was an interpretation in recently by Smirnov and Zamolodchikov about all these other ones. That previously, essentially, there were ambiguities in your S matrix bootstrap axioms that you normally would ignore just by choosing some minimal solution. Also, let me mention that these all look bad, but because of how they behave at high energy, but this is just a bad basis for these shifts. You can introduce another, if you want, another way to rewrite this by taking an infinite combination where it will be regular at high energy. And so this suggests that there is an infinite family of deformations of your integral models that will preserve integrability. And the interpretation of Zamolodchikov is that these shifts are in one-to-one correspondence to deform the theory. Now with this is your integral models, and you deform it with something like T-Bar, but that you can construct out of your higher spin currents. And here I'm writing T-Bar just because so it's only for spin 1 that theta enters into the equations of motion for both T and T-bar. But normally you will get 2 different fields here. Maybe I should explain this notation.
Yeah, maybe because these T's are, they are somewhat close to 2d4, d6, right?
Yeah. Oh, yeah, exactly. Let me explain it better. Yeah, maybe just anywhere.
Maybe you can take some questions.
Yeah, are there any questions? Yeah.
The symmetries. In this case, is this the only what you have on the left-hand side for the moment, or what do we have? What is constraint in this case for this curve?
Due to Young-Baxter, you won't get a constraint, an additional constraint from these phases, because these are just scalar factors that you multiply everywhere, irrespective of quantum numbers or types of particles.
Yes, but in this case, you don't need any bootstrap equations or whatsoever.
In which case, sorry?
Like in this case, for sure the symmetry.
Yeah. So the idea here is that you assume some symmetry, and if you have a non-abelian symmetry, well, you need to solve a Young-Baxter equation and try to find the solution of the S-matrix bootstrap. And then once you have a solution, however, you can multiply it by any of these factors, and it will still be a solution of to the axioms.
And by anything with sums and those equations, you can regularize.
Yeah, so you can write it as some more regular factors that will introduce just some additional poles on some unphysical sheets. They will not change your mass spectrum, and these regular factors that still behave well at high energies formally are an infinite combination of these deformations. Well, so in an integral model, in general, you have some conservation laws of this form, but then, okay, you will have also some that come in the same way. Starting from the CFT, you have some that come from the other sector. And as what I did at the beginning with T-Bar is that for any pair of currents, you can construct these determinants, and they will have nice properties. So you can do, in principle, a determinant out of two currents out of this infinite set, and you can take any pairing with different spins also. But this will break rotation symmetry. So this will be a deformation that you wouldn't see in terms of deformation of an S-matrix of a Lorentz invariant theory. But so the conjecture that was also checked and is that deforming the theory with this operator, let me write it formally as like this, minus the thetas. So this will, it was checked that this will preserve your integrability, so you can correct your currents, and in presence of this irrelevant deformation, they will remain conserved currents, and that this corresponds to the dressing of the S-matrix in this way. So it gives you a sort of understanding of the space of integrable quantum field theories. And yeah, I think I can conclude here. And are there any questions?
I may have missed this, but I thought the original arguments were based on the UV limit of the thing being the original CFT with all these conservation rules.
Mm-hmm.
But now you're perturbing by an irrelevant operator.
Yeah.
The UV limit is not the CFT.
Yes.
Is there some get out or something?
No. So if you perturb with something like this, you will spoil the UV limit. So if you...
Right. Well, you started off with a bunch of conservation laws in the CFT.
Yeah. So then... Yes, so then, okay, I'm assuming that out of this argument about perturbing CFTs, you can construct integrable models that have conservation laws everywhere, also in the infrared. And then another question is that now I can add some other perturbations to them that now are irrelevant and would still conserve these currents. But these perturbations will know nothing about the original CFT.
So there is a bit of a jump.
Yeah, there was a jump, yes. but I thought, well, I wanted to try to connect integral models with CFTs, which you heard about in the school. But then, yeah, the last part was connecting integral models with T-Tbar.
More questions? If not, let's thank Andrea, but also all the speakers and tutors of the school for their very nice work. Let's give them a big hand.